Our universe thrives on energy. It's the force behind stars, planets, and even life itself. This energy often comes from atoms, the tiny building blocks of everything we see and touch. Atoms are incredibly small. Imagine a grain of sand, now picture something millions of times smaller. That's the scale we're talking about. Inside these minuscule atoms lies immense power. This power can be harnessed, for better or for worse. The story of the hydrogen bomb is a tale of this power, how we learned to unlock it, and the consequences that followed. Before we delve into the hydrogen bomb, we must first understand its predecessor, the atomic bomb. The atomic bomb utilizes a process called nuclear fission. Imagine splitting a tiny atom apart. When this happens, a tremendous amount of energy bursts forth. This splitting, this fission, is what powered the atomic bombs used in World War II. The world watched in awe and horror as this power was unleashed. But there was another, even more powerful process waiting to be discovered: nuclear fusion. The atomic bomb, with its awesome and terrifying power, cast a long shadow over the world. It was a weapon born of fission, the splitting of atoms like uranium or plutonium. These heavy, unstable atoms, when bombarded with neutrons, break apart, releasing energy in a massive explosion. The cities of Hiroshima and Nagasaki stood as grim testaments to this power. Yet, even as the world grappled with the implications of the atomic bomb, scientists were already on the cusp of unlocking an even greater force: the power of the stars, nuclear fusion. Unlike fission, which splits atoms, fusion combines them. The hydrogen bomb, a weapon of unimaginable power, is the result of this process. Imagine the sun, a giant ball of gas, generating heat and light for billions of years. The sun's energy comes from fusion, specifically the fusion of hydrogen atoms into helium. The hydrogen bomb replicates this stellar process on Earth, albeit for a fraction of a second. The result is an explosion far more powerful than any atomic bomb. The key players in this fusion dance are light elements, primarily isotopes of hydrogen called deuterium and tritium. Deuterium is hydrogen with an extra neutron in its nucleus, while tritium has 2 extra neutrons. These isotopes are abundant on Earth, particularly in water. Under immense pressure and heat, these hydrogen isotopes are forced to overcome their natural repulsion. They fuse, creating helium, and releasing a neutron and a tremendous amount of energy in the process. Creating the conditions for fusion to occur requires a carefully orchestrated sequence of events. This is where the atomic bomb comes into play. The hydrogen bomb actually uses an atomic bomb as a trigger. This fission explosion generates the initial heat and pressure. The heat from the fission explosion is so intense that it releases X-rays, which travel faster than the expanding fireball. These X-rays compress and heat the deuterium and tritium fuel, creating the extreme conditions necessary for fusion to begin. The fusion reaction releases an immense amount of energy in the form of heat, light, and radiation, resulting in a thermonuclear explosion far exceeding the power of the initial fission reaction. The development of the hydrogen bomb was shrouded in secrecy, a testament to the Cold War rivalry between the United States and the Soviet Union. In the aftermath of World War II, both superpowers raced to develop this new weapon, driven by fear and the pursuit of military superiority. The first hydrogen bomb test, codenamed Ivy Mike, took place on November 1, 1952, on the Enuatak Atoll in the Pacific Ocean. The explosion, equivalent to thousands of atomic bombs, vaporized the island and sent shockwaves around the world. The hydrogen bomb, a weapon of unprecedented destructive power, forever altered the geopolitical landscape. The concept of mutually assured destruction, or MAD, emerged, where the use of such weapons would lead to the annihilation of both aggressor and defender. Yet, amidst the fear and uncertainty, the science behind fusion offered a glimmer of hope. If harnessed for peaceful purposes, fusion could provide a clean and nearly limitless source of energy for the world. Fusion research continues today, with scientists striving to achieve a controlled, sustained fusion reaction, a miniature sun on Earth that could power our cities and fuel our future. The story of the hydrogen bomb is a stark reminder of humanity's capacity for both innovation and destruction. It is a tale of scientific brilliance intertwined with the sobering consequences of unchecked ambition. By understanding the science behind nuclear fusion, we can better comprehend the power we wield, and the responsibility that comes with it. This knowledge is not just for scientists and policymakers, it is essential for all citizens of the world. As we venture further into the 21st century, facing challenges like climate change and resource depletion, the pursuit of peaceful fusion energy takes on even greater urgency. By unlocking the secrets of the stars, we may yet find a brighter future for all humankind.